is okay. Very excited to have Roman Walters, an applied math professor at Northeastern. He's leading the head of the lab on geometric learning, and he's an AstroAI partner. So we've been very happy to work together recently, and we'll continue to do so. And he will tell you a lot about equivariant networks. Oh yeah, we have to get it that. So yeah, very excited. You can take it away when we get rid of that blue thing. Okay, here we go.
Okay, thanks for having me. Yeah, it's been really, so like I work on core deep learning methods, but there's this, intersection with a lot of scientific domains. And one of the fun things for me is getting to meet people like Cecilia and learn about things that I don't really know that much about, like Astro, and then have some conversation about the way symmetry can, link things together, and we can develop methods to improve performance in these domains. So mostly in this talk, what I'm going to be talking about is kind of like a survey of various applications that I've found for this methodology. All right, okay, so deep learning, at scale has been doing amazing things, and what I see my work is doing is targeting some of the deficiencies in modern deep learning algorithms. So one of the big ones is limited generalizability of models. So I work on dynamical systems, and a lot of the dynamical systems and sciences that you focus on, when you train neural networks on them, you find that they have very limited generalizability. So I'll talk about fluid mechanics later. Fluid mechanics are underlied by Navier-Stokes equations, and you might think that if you train a neural network on some fluid flow data, it will learn the Navier-Stokes equations, and what you find is that it's absolutely nothing of the sort, and that if you change the parameters very slightly, like make the fluid a little more viscous, or like change the boundary conditions, or do anything that alters the physical system in absolutely any way, the neural network completely collapses, unless you do something to actually make sure that it will generalize. Another one is data. So like these, I'll just talk about, like you have these huge, you talk about scaling these days. So if you have lots of data and big models, the neural network can learn anything, right? Now I'm interested in a lot of like scientific domains, and people are often, hear it weird, but a lot of these scientific domains are actually sort of small data domains, because even though we're collecting like terabytes or petabytes of data from these large scientific instruments, the problem is the size of the distribution, right? And the dimensionality of the problem is so large that actually that data sample, no matter how many bytes it is, doesn't actually give you good coverage of the distribution. Like language is big, but actually the whole internet gives you good coverage of human language distribution. Whereas various data collected from a telescope isn't giving you great coverage of the physical system you're trying to study. So we're sort of in this small data regime. And the last thing is inconsistency and lack of guarantees. So this is sort of the black box model problem. You train it, you don't have guarantees in the outputs, you can't understand what it's doing. So, so my work is about addressing these problems, and the not unique solution, but the way I approach these problems is through the lens of symmetry. And so the idea is that we're going to take the symmetries in the system and we're going to incorporate them into the neural network. So this is kind of, I think of it as like a hybrid solution, right, between classical mathematical modeling, in which you try to take these first principles in order to develop like a mathematical model of the system, and neural networks learn everything from data. We're not going to learn everything from data. We're going to assume we understand the symmetries of the system, since we've known them probably for several centuries, instead of like working. Otherwise, the neural network works very hard for a very long time to probably never actually learn those symmetries, right? So we'll just use that we already know, and then we'll build neural networks that are going to work a lot better and on all of these problems. All right, so here's my overall like pipeline that I, literally show this slide to when I meet with some buddy who works in some domain area, right? Which is that we're going to say, okay, what problem are we trying to study? What are the first principles models that we have for that? What symmetries do those models contain? These two can actually sort of switch places, since like when you're developing differential equations for a system, you usually start with the invariances and then find differential equations that satisfy them. But you also could take differential equations that you found, maybe just like through some like regression techniques, and you can do some perturbative analysis to extract the symmetries of them, right? And then we're going to build neural networks that are constrained by those symmetries, that have the symmetries within them, and then we're going to train those neural networks to model the system, and the resulting models we get are going to generalize better and learn from much less data. All right, please. Okay, all right, I often talk to like a pure CS audience, so they don't know group theory, but if you guys are physicists, you already know this. Okay, so this is how I talk about symmetry. So you have group theory and you have representation theory. So here is an example of a group that represents an abstract type of symmetry. This is the cyclic group on 4 elements. It contains 1 r squared, r cubed, and it has a multiplication. And when you multiply up to r to the 4th, you go back to the beginning. So it's like a little cycle, okay? And this is the abstract group template. That is all of the data that is contained in that abstract group, right? It's not, doesn't look like a symmetry, right? But then a representation of this group is like an instantiation of this abstract symmetry type on some data space, let's say, right? So for example, what could be one representation of this? Well, we'll take that generator R and we'll map it to this 2x2 matrix. So in the abstract case, R is a thing that when I do it 4 times comes back to 1. So what's a thing that when I do it 4 times comes back to 1 on R2? Well, a 90-degree rotation matrix, right? And so you can check that this represents that abstract group in the sense that if I take this matrix and multiply it by itself 4 times, I'll get the identity matrix. So now I have a linear algebra realization of that abstract group. But that is not the only representation of this cyclic group, right? I could also have a 4-dimensional representation where I map this generator to this 4x4 permutation matrix that permutes the standard basis vectors of R4. And if you take this permutation matrix and take it to the 4th power, that will also get me back to identity. Okay, so same group can have many different instantiations, infinitely many different realizations in terms of data, in terms of matrices, and that takes the world of group theory into the world of linear algebra, where all of our favorite tools apply. Okay, so this is sort of the glue. This is how we talk about how does symmetry apply to problems that we can apply neural networks to. So we often talk about functions being symmetric, and we say that they are equivariant. So this function f is supposed to represent the task or the supervised learning problem that we're trying to learn. So we take some input space to some output space, okay? And we want to apply a neural network to that, but there's no neural networks in sight yet, just we're thinking about the task itself. So if you look over here at this picture, I'm giving the example of f being a segmentation task. This is a classic computer vision task. The input is x, this picture of the tiger walking in front of the grass, and then f, I guess I'll just like walk over here and leave, right? This is the output, right? So now instead of colors, the pixels are labeled by what they are. Like, tell me which pixels are part of tiger, which are part of grass, which are sand, right? And the thing you're supposed, so this is a task we could train a neural network on, but let's observe that it has a symmetry, which is if I take the image and I rotate it, and then I apply segmentation, that's the same as if I apply segmentation and then rotate it. So the task of segmentation commutes or intertwines the rotation action. So formally, we say that segmentation is equivariant with respect to rotations or translations or scales, right? The tiger is a tiger, no matter how we look at it. All right. Okay, so now that we have observed that symmetry in the task, the next question is how do we build a neural network that incorporates that symmetry into it? Okay, so here's my picture of like a really basic neural network. Okay, here's our input space, our D in. All the way over there is our output space, our D out. Okay, and here are all the hidden layers of my neural network. I do a linear layer, I multiply by a matrix. I do a nonlinearity, I do a linear layer, a nonlinearity, and I go all the way through to the output. That's my multi-layer neural network, okay? And the new part that isn't on this picture before we talked about symmetries is this group G. So in the example before, this would be rotations, right? And the problem before we started thinking about neural networks, we knew that this symmetry group acted on the input and output space, that it rotated or transformed those images. The new part that we don't know is in these latent spaces, these hidden dimensions that are just the neural representations of these images, we don't know what a rotation means. They might not even be images, right? And so that's a decision that we have to make. So we use that fact that I said earlier, where a group can have many different instantiations, many different representations, and we choose from among the group representations in order to create these neural representations. So that's just like a collision of terminology that like groups have representations and neural networks have feature representations. And in this case, and only in this case, that's sort of the same question, is what group representations should our feature representations have? So that's a choice we have to make. So here's an example. Let's suppose that I will have this layer be R2 and this layer be R4. So those are laughably small dimensions to the hidden layer of a neural network, but just for an example, right? Okay, and so now we will choose that the rotations act on this hidden thing by 2 by 2 rotations, which is the example we saw before. And we'll act on this R4 by this permutation representation. Okay, and now we can ask, what would be a linear mapping which would commute with these rotation representations? Okay, and you'll get this answer, right? And so what that means is, it's just a simple sort of linear algebra question, right? Normally, if I have a linear layer in a neural network going from an R2 to R4, I have an arbitrary 4 by 2 matrix. So there would be 8 trainable weights there, right? But when I impose this constraint that I have to commute with these 2 matrices, right? What you see is this 8-dimensional space goes down to a 2-dimensional space. These weights A and B get repeated and shared in the network. And so whenever we talk about like equivariance, that usually results in what people call weight sharing or weight time. So if you like, you can work out the if and only if on this exercise. That there's this kind of weight sharing, and there's the commutation relation. If you want, you can see the symmetry commutes with the linear layer. Yeah.
I'm just reading some of my representation theory, but is it unique in terms of representation for a given dimension? So for a given RB in the intermediate layers, do I have a unique representation?
No.
Okay, so then I don't have a unique weight sharing operation either.
No.
What's the implication of the choice that you're making in the representation for a given RB?
Yeah, it's a great question. I mean, you have to make that choice. So like,
What implication does that have on the task at hand and the actual application?
we don't know. I mean, I don't have a theory of it. What it becomes, it's like saying like, okay, design a neural network to solve that task. Should the hidden layer be 128 dimensional or 256? Right? We don't know. We call that hyperparameter tuning. We have to run the model both ways to see what works better. Right? So now we took that problem, called the hyperparameter tuning problem, and I made it worse because I just said to you, not only do you have to pick what dimensionality is, but you have to tell me how the group transforms it. So there's an additional degree of flexibility that we need to say. We need to say, what is the transformation property, right? They're not just activations anymore. They're vectors that live in a group representation, and I need to choose which group representation. So I said it in a way that makes it sound hard and challenging, which it is, but also it's an additional flexibility that you get to design your neural network. So maybe through the right choice, you can realize better performance. But I would say which one to choose in a principled way is an open problem, which is great. Yeah.
Maybe you're gonna go to this next, but
Yeah.
this is only for the linear.
Oh yeah, great question. Yeah, this is for the linear layer. So yeah, the thing like underneath is telling you, right? So I've just told you how to make this layer commute. Remember, we want this whole function to commute with symmetry. Symmetry then do the neural network equals neural network then symmetry. You want them to commute. And I just told you how to do one layer, right? But the fact is, right, if I make all of the layers commute with the symmetry, then the whole network commutes with the symmetry. So you can just like prove that to yourself quickly, right? Like if I can switch the action with one thing, I can keep switching it all the way down the line until it reaches the end. So I just told you how to do the linear layer, but of course the nonlinear layers also need to commute. And that's not necessarily a simple problem either. That you have to think about the constraint, and that depends on the representation choice, which is maybe one answer to your question, right? So for the permutation representation, I'm showing that ReLU would commute. ReLU acts on each component of the vector. So if I permute the components and then do ReLU, that's the same thing as doing ReLU and then permuting them. But ReLU doesn't commute with 2D rotations, right? If you think about it geometrically, ReLU takes any vector and projects it to the first quadrant. So if you rotated out of the first quadrant and then do ReLU, that would be different as doing ReLU and then that. So I'm showing this is a radial rescaling function, which is a nonlinear activation I could choose that would commute with rotation, since it only depends on and affects the magnitude of the vector, not its orientation. So, good question. Okay, and then here's the overall picture of what this modeling looks like. So when we take a neural network, we define a model class, and then we optimize using stochastic gradient descent from a random initialization and using data to hopefully converge towards the true function. Okay, so in my cartoon picture, the approach that I'm suggesting here says that we're affecting the model class. Right? So we're parameterizing a space of equivariant functions, a space of neural network models, all of which are equivariant, even at initialization. And then we are performing optimization within that subspace to find the true function. Do I have another? No, okay. So in other words, in principle, you can intuitively think about why does this work? Because we know the true function lives in this smaller class. So we have an advantage to searching for it because we have started already in that smaller class. So instead of like searching the needle in the haystack, we're searching the needle in like the smaller haystack. We already know it's in this part, and so that gives us an advantage. That's the principle. Okay. So that's just like my intro. Are there any questions before I go on into all the applications? Yeah.
Sure, I mean, so sometimes people in autoencoders try to enforce some sort of interpretability in internal layers, like meet a parameter system, the viscosity or the mass.
Yeah, yeah.
And how does that play with the notion of having to enforce permutations on the latent state and like that? Like then it's sort of hard to assign interpretability to some of those latent parameters.
I would say that this kind of, so, okay, in terms of like, it's a good question, and there is work on this. So my view is that what I'm doing is I'm taking latent representations and I'm enforcing geometric properties on them. So I don't know what my hidden layer is exactly going to mean. I can't say like, oh, look, the autoencoder learned to factor all the objects and give me like momenta and positions, right? I'm not telling it to do that, but what I can do is I can design a space where there are permutation symmetries and there are various vectors that should transform the way positions and momenta should, right? And so I'm sort of providing slots with the right geometric type that possibly the model can use to learn those properties. So like, if I know something about the physical system, I can design a latent representation that matches that geometric property. And we do see corresponding improvements in performance and in interpretability. You can often see what you get. Okay, so here are some application domains in which we've applied this principle. So fluid dynamics, trajectory predictions for vehicles and pedestrians, materials, radar modeling, robotics, and this cool computer vision example. So I'll talk about as many as I have time for. Okay, so here's just a case study in turbulent flow modeling. So this is like a growing area. In particular, this has become like a hot area because modeling fluids is so computationally intensive, but the idea to be able to do it like many orders of magnitude faster using neural surrogates is extremely attractive to people, right? Especially like, for example, this is sort of indicating like a weather type problem, right? This is not a problem that you can easily solve using direct like numerical simulation because the system is so partially observed, right? I don't know what like the flow looks like many feet below the water to a high resolution, which is going to drive my predictions off very quickly, right? So a neural network has a particular advantage in modeling systems that are partially observed because it can infer sort of missing inputs and also robust to sort of the noise that's in the observations that we have. Okay, but what I'm showing here is just the scaling symmetry. So this is the scaling symmetry for Navier-Stokes equations. If I have removed any sort of boundary conditions or internal forces, right? And like scaling symmetry is obviously very key to understanding fluid flows, right? Like if this if this scaling law didn't hold, then we couldn't build wind, like we'd have to have full-size airplanes to figure out how they work, right? We could not use wind tunnels, right? There would be no such thing as a scale model, but the dynamics would be fundamentally different, right? And similarly, I can't like study like a dinosaur by making a tiny dinosaur because the biomechanics don't scale between those two, right? And so like scaling is extremely useful. So my goal is to take this scaling law and put it into a neural network, and then apply that neural network to fluid flows and see if it works any better. Okay, and now here's how I do it. Okay, so this equation is 2D convolution, which is, since is one of like the backbones of computer vision models, right? So here we take some image, V1 as input, and we apply some kernel function K to every location of the input, and that gives us the output image, right? So it's just a straightforward, discrete cross-correlation convolution operation. Okay, and this is famous as a layer that actually has some symmetry, because if I shift the image over by 1 pixel and then apply the convolution, I will get the same output, but shifted over by 1 pixel, right? And so actually we're already thinking in terms of symmetry, and why is that? Why did we get that property? And you can kind of think, well, obviously I get that property because the way this operation works is it applies exactly the same kernel at every input space of the image, right? Now, if you think about it, that actually connects back to what I was saying earlier when I described the intertwiners that give you equivariant maps on the layers, right? Where we saw that weight sharing pattern, right? If you think about the expanded matrix that corresponds, so convolution is a linear operation, in fact, so therefore it has a matrix. And I think about the big matrix that corresponds to a convolution operation, it's got the same kernel weights repeated over and over and over again, right? And that actually is, right, the solution to the problem I showed earlier. In other words, you could reinvent convolution if you wanted by asking, what is a linear operation that commutes with these shifts? And you would get this particular weight sharing pattern, and then you might realize that it corresponds to applying a kernel function across the whole input. But the main thing is that we're taking that kernel and translating it across the whole input, and that's why it commutes with translations. So like, being brave and generalizing, we could say, if I want to commute with a scaling law, what I need to do is I need to take a kernel function and not just translate it across the image, but also rescale it across the image. Okay, and so that's what I sort of got down here, right? We're summing not just over all the shifts, but we're also summing over the different scales that we see in the image, okay? And obviously it's ridiculous to write sum over all lambda over the positive integers. So in practice, there's some, we choose a couple of different scales and we approximate. And then what we see here is, so this is this anisotropic scaling law from the last slide that the fluids observed, where we scale space by lambda, time by lambda squared, and velocity by 1 over lambda. And here we have directly input that into this scale convolution operation. And so this gives me an approximate scale equivariant operation, since I'm scaling and translating the kernel. Okay. Okay, and so here's some results. So here I'm applying this to sea surface flows. Okay. And I'm applying this equivariant network compared to a non-equivariant network. Okay, and we see some interesting results. So first of all, we see that just like in terms of the RMSC, the actual prediction of the velocity vectors improves when we incorporate some of the system symmetries. This is showing results for, so here's the truth. This is the non-equivariant baseline, and then here are various equivariant models to various symmetries like rotation and scaling. One of my favorite results here is this spectrum column. So one problem with neural networks applied to fluid flow data is that they often, they can give you good, I remember the first like early papers on fluid flow data, they trained the network to simulate the flow, and they got some very beautiful like animations, right? And then they talk to the fluid experts and they say, okay, well, let's take a look at like the energy spectrum for the fluid, and then it was nonsense. And so they said, we've developed a method for simulating fluids for 3D animation. That's what this is for, right? So part of what we're doing is we're saying, if we can incorporate some of the physical symmetries of fluid flow into the neural network, does it actually result in higher physical fidelity? So partnering with like our domain, so we now measure the energy spectrum of the fluid and compare the energy spectra. And then we have this ESE column, which is measuring the energy spectrum error. So how well did the energy spectrum is aligned? That's just one number. We could look in far more detail about like how various scales are preserved, right? But what we see is dramatically improved performance in the energy scale. So by incorporating symmetries of the system, we get much better energy, much better physical fidelity in terms of the actual energy spectrum of the fluid. Yeah.
So each of these that you're showing is a different symmetry group, or you cannot combine them?
It's a good question. Yeah, so in this case, we're modeling symmetries separately. So yeah, this is like the full like symmetry group of the equations over all of these. And so I think it is a natural question. What if you combine them all? And I will tell you what happens. So it's not clear why, but there's kind of a saturation in the learning. So as you combine various physical symmetries together, this sort of improvement in performance sort of flattens out at a cost of increased computational complexity. And that's kind of an open question in ongoing work, but it alludes to kind of a cool and subtle point earlier that I glossed over when I showed you the needle in the smaller haystack, which is that applying, just because the true function lives in this constrained space, does not necessarily mean that it's easier to optimize the neural network in the constrained space. So there's some trade-off in terms of imposing constraints on the optimization problem, where yes, the constraints do reflect the true function we want, but could interfere with neural network optimization.
But so, just one quick follow-up.
Yeah.
So if you just, maybe it doesn't improve the learning, but the end product would be symmetric under the other symmetry that you expect. Like if you do scaled symmetry, and then it won't be rotation invariant.
Right.
If you didn't train it to be, and that would be something you would like it to be, right?
Correct, yeah.
Okay.
Yeah, so ideally you would combine all these symmetries, but there's some trade-off where when we have really big symmetry groups, the performance starts to not get worse, but plateau, which
would apply them sequentially, solve that.
I guess I don't, maybe, but I don't know a way to, because at least like this approach that we're following, like applies the symmetries at the beginning, like before we've done any training, like just like working on our little like textbook, we figure out what is the new parameterization for layers. So we can't kind of bring them on later. They're not like losses that we compute. Like sometimes people do like loss annealing, where they have a schedule that like applies various like constraints or losses at various times. These constraints are applied a priori, so I can't like turn them on or off in a simple way. Anyway, okay, so it's a very like interesting and subtle question. Okay, so here's one recent evolution of this work, right? Which is what happens when symmetry is not exact. So oftentimes when I look at data, real world data, I don't have the exact symmetry holding that I want, right? That can occur for various reasons, right? There could be external forces or boundary conditions that don't preserve the symmetries of the whole equation. My data could be collected in ways that are very biased. I could have like noise in the observational model that doesn't actually reflect the symmetries, but I'm training my neural network on it, right? Or this like ducky, this ducky comes from like an actual robotics manipulation problem, right? Where we were trying to pick up objects, and there was this, see the checkerboard background underneath it? We're like, well, if the object rotates, then the robot should rotate. That makes sense to us. So we enforced this rotational symmetry in the environment, but we didn't realize that the checkerboard background wasn't rotating. right? So there was symmetry breaking in the observation, right? Which was not actually part of the symmetry in the state that we are interested in, right? So you can have these kind of like factors where the symmetry still exists, right? But there's some sort of factors that are breaking symmetry in the observation that you need to account for. You don't want to throw, the typical like knee-jerk response for deep learning is like, oh, if the inductive bias doesn't fit perfectly, you should throw it out. In fact, there's people who really hate all inductive biases. They're like, just scale the model will learn everything, right? But what we've shown in this paper is that just because there's some like factor that messes up the symmetry a little bit does not mean you want to throw all of the symmetry out with the problem, right? You do best if you try to account for the symmetry breaking and still keep the symmetry in the problem. I would click. Okay, so here's a picture of how you adapt the equivariant convolutions that we discussed to have some symmetry breaking in them, right? I think the picture tells a pretty good story. So here's my 7x7 convolutional kernel with no constraints for rotation. Here is a simplified, this is if I assume a trivial representation on the channel input and output. If I choose that case, I can produce this really simple visualization for you, where you can really see what a rotational symmetry in a filter looks like. Please do not think that all rotational symmetry produces rotational inputs. This is kind of a special case, okay? But in this case, right, what I'm doing is I'm taking this rotationally equivariant convolution operation, and I'm inserting these parameters WL of Y, and these are symmetry breaking parameters, and we initialize them to be basically the identity. And with the parameters initialized as the identity, I have a model which starts with no symmetry breaking at initialization, but as it trains, those symmetry breaking parameters can learn to break the symmetry in the model, okay? And we end up with a picture like this that is approximately equivariant or approximately invariant to rotations. I'll just comment like briefly mathematically on like what's going on here, and I'll give you the 2D convolution as an example. So in the 2D convolution, right? Yes.
I think we have a question online.
Sure, yeah.
Yeah, Aston, if you wanna.
Okay, so I want to understand a little bit about the approximation case. I mean, there are two ways in which I can understand that this is an approximated symmetry. One is just establishing a measure and saying, yes, even if you look at the example, you realize that most of them is symmetric or something like that. So there's a slight variation of the symmetry. But another way in which I can think of it is that this is a asymptotic symmetry in the sense that this is symmetric at least in a region of the space. So there is, in the second case, unlike in the first case, there is a notion of locality in the picture. The first one is just a measure established globally. So I want to understand which cases you can gather with this.
I see. Yeah, so the question is about local versus global symmetry in the domain and what kind of approximation this is capturing.
Yes, it is. I mean, this is an approximate symmetry, but in the example you're showing here is in the two sense. It's
right.
Locally it is and globally it is. So I want to distinguish the two cases and to know in which cases you can apply this.
Right. Local and global symmetry is interesting. I think it depends is the short answer. So let me say quickly the example I was going to give, and that can, I think, help answer the question. So the 2D convolution cases shift equivariant. Why? Because I apply the same exact kernel to all locations in the input, right? How do you break or relax that symmetry? Well, you could imagine having a kernel that's applied across the whole image where the values in the kernel can depend maybe in some constrained way to the location of where you are in the image, right? And so that would be a kind of local symmetry breaking where there would be certain places in the domain of the image where you would want to have a slightly different value of the kernel, right? So we see that, for example, like in our fluid flow, when we have like certain boundary conditions, right? It interferes with isotropy. So we see the rotational equivariance falls away near the boundary. So having sort of a local relaxation that lets us relax rotational equivariance near the boundary helps in modeling. So I would say it's largely a local relaxation.
Okay.
Does that help?
Yes, yes. Okay, thank you.
All right, here, okay, so here's the results. So here is, so this is a, okay, so this is a flow modeling task where we have we've broken the symmetry of the problem by adding some external force that is tied to the frame. So if the neural network is sort of aware of the sort of orientation of the coordinate frame, then it can use that to improve the predictions and understand what's going on better. Okay, and then this chart is like one of my favorite charts. So let me explain what's going on here, and you can see why this modeling works well. Okay, so on the bottom, I have the data equivariance error. Okay, so what I mean by that is I mean how much symmetry breaking is there in the task. So this is fluid data that we simulated. So what it means is we have control over how large the force is that is breaking the symmetry of the problem. So I can modulate all the way from a problem where things are perfectly symmetric to a thing where things are super tied to the actual orientation of the frame. Okay, this blue line is and then the y-axis is how constrained or relaxed the model is. So how much symmetry breaking did the model learn, right? This dotted line is y equals x, and perfect modeling would mean we're on that line. It means however much symmetry breaking the problem has, that's how much our model learns. So we want to be on that line. Okay, this blue line is an equivariant model with no relaxation applied to that problem. So notice that as I dial up the amount of symmetry breaking in the problem, this model is forced to stay at 0 equivariance error, which means it stays perfectly symmetric. Okay. On the other hand, you could take the approach that you want to throw the inductive bias out the window. The model should just be able to learn how much symmetry is the problem. We shouldn't think about symmetry at all. We should just build a neural network, train it, and let it learn. Okay, so that's the yellow line, right? So I think it's interesting to note, first of all, the yellow line does not adapt to the level of symmetry breaking in the data, right? And it also doesn't acquire perfect symmetry when the data is perfectly symmetric, right? It does have a slight, like, the slope is positive, so like the more symmetry breaking there is, the more the model learns it, but it fails to perfectly learn symmetries when they exist, and it fails to like learn directionality in the data when it exists, right, perfectly. This green line is our model. So I'm particularly pleased by how close the green dot is to the blue dot down here, right? This is saying basically, and actually you can prove this, that if you train a relaxed equivariant model with symmetry breaking in the weights on data which is perfectly equivariant, then the model, those weights will stay at basically identity, and the model will stay equivariant. So there's sort of no cost to adding those relaxations. They just won't be used. They're just extra weight parameters. So you have more parameters, a little inefficient, but it won't cost you in terms of performance. And then it does basically, because of the explicit sort of representation of symmetry breaking in the model, it does a much better job adapting when that symmetry breaking exists in the data. So we have and there's room to grow. We're not on that line, but yeah.
So, I mean, how are you measuring equivariant error? I could imagine several different ways of measuring that, and your green line outperforms the orange line when you measure it the way that you may have built it into your network to measure it. But like maybe on some other metric of equivariant error, you're not beating.
That's fair. Yeah. It's not a trivial thing to sort of measure equivariance error. If we go way back, so yeah, maybe we'll take that offline, but if we go way back to the beginning, I have this equation like f of g of x equals g of f of x. That's these two things are equal means the equivariance error is 0. So what we do is we subtract one side of the equation from the other, say it's 0, right? Now we put magnitudes around it, and so we measure sort of like how close that term is to 0 in order to construct it. But it can be a difficult thing to measure, like, because you might have x in your data set, but g of x might not have in your data set, so you don't have f of g of x. So there can, depending on how much control you have to generate labels, here it's okay with a simulator, but it can be a little complicated actually to measure data symmetry from a distribution. It's not a trivial problem, like, yeah. Okay, let me think. I have, what time do I go until? What? Yeah, I'll mention this briefly, especially since we talked about global and local. So this is like a little bit of less of a scientific application, and I'll tell you how we got onto it. So we did this first thing on simulating fluid flows in an Eulerian modeling setting. So we were simulating the velocity field over like a grid, right? And then, of course, there's another like big way to simulate fluids, which is the Lagrangian modeling scheme, where instead of simulating vectors on a grid, you actually simulate a bunch of particles, right? So we tried to do that, but it's super computationally intensive, right? Because you need a lot of engineering to get this right, because you need a ton of particles and it's very hard, and we didn't have the hardware. So we said two things. First of all, what is a particle system with fewer particles in it, in which to some extent the kinds of symmetries that apply to flows still apply, right? But actually like contains a lot of partial observability and unknown dynamics and stochasticity that actually makes it even better for modeling using neural networks. And so we actually have a collaborator at the University of Michigan who studies traffic flows using fluid models, you know, not literally fluid models, but basically there's this split, right, where people have all these models sort of inspired from flow dynamics for modeling highways. And you actually go and like look at videos of highways where you can see like the shock waves moving through traffic cones, and it's kind of amazing. But okay, here's a picture of something that we want to model. So the goal is to capture some kind of local symmetries. The idea is that broadly speaking, the interactions of these are some cars at an intersection is highly local, right? And it doesn't, for the most part, depend on like the absolute like cardinal directions in space. It really just depends on the relative orientation of cars. So for whatever reason, in this example, this like green car is like kind of cutting off that red car as it like changes lanes, right? And notice this same situation sort of occurs over here. And so I'd expect basically the same kind of dynamics to occur up to a rotation, despite the fact that the other actors in this picture are not in the same position. So that's what we want to enforce with the model. And this sort of says basically the kind of weight sharing that we were doing in the last project, this can also be applied in this situation. The like wrinkle is that instead of using grids, you have to do things with sort of continuous kernels. So you have to just ask what are weight sharings for continuous kernels, and you can produce some pretty pictures of sort of the map that corresponds to. And so now you work that out, and now you have some continuous version of these neural networks with these symmetries. And here is sort of the result. So in this case, I want you to look at this red car, which is turning left, right? And here is the exact same scene, but turned about 130 degrees, okay? And ideally, if I'm, you know, in a self-driving car that is predicting the motion of cars around me so as to avoid colliding with them, ideally those predictions would be invariant to, you know, what the absolute like positions I'm predicting in. Okay, and here is a non-equivariant model applied to this prediction, right? And you can see actually that not only do they get the prediction wrong, right? The output of the model actually depends on the rotation of the frame. So depending on how the data is input into the model, this model will predict either a right turn or a left turn. So I can get completely the wrong answer depending on how I'm modeling it. And here is our equivariant model, right? So notice the equivariant model's output is not exactly correct, right? But it is entirely consistent. If I rotate the input, I will get a rotated output. So it succeeds in to some extent, I think, solving a little bit of that black box issue of the neural network, right? Where I can not say perfectly where all of the properties the neural network have, but I can guarantee that it will be consistent and not depend on the orientation of the frame.
So driving down the left is bad in any case, is what you're saying.
Yeah, maybe if you wanted to if you wanted to generalize to other countries all within one model, that would be. Okay, here's another application. So this is a collaboration with many students and Robert Platt's lab at Northeastern. So they work on robotic manipulation. So Rob was in the audience at a talk I was giving a couple of years ago on fluid modeling, and he said, can we use those symmetries for manipulation problems in robotics? And that kind of developed into a pretty big application for us, in part because, first of all, you absolutely can. And second of all, it turns out like fluid modeling is not the perfectest problem for equivariant modeling because it's very high dimensional, right? So like, do symmetries help with fluid modeling? They help a lot, okay? But it's still a very hard problem. Whereas in many cases, problems of robotic manipulation are so low dimensional that when you account for the symmetries, you account for like a lot of the difficulty of the problem. And so with fluids, you go from very hard to hard. With robotics, you often go from hard to trivial or hard to easy. Okay, so like in this, maybe I'll show some example, right? So let me talk about how the problem is stated, right? So here's the state of the system. We have the block and the gripper. The problem is to pick up the block or something like that, right? And we have some actions. So I believe, or maybe if I press down, right? So here the action is to push the block, right? And here we have this symmetry commutative diagram that every problem I work on has, right? Where notice we have the following equivariance, which is that if the robot pushes the block, right, from a given state, I end up in this new state, right? And then if I were to rotate the block and also rotate the push, right, then I end up with the rotated version of the state. So I can go either symmetry, then compute the transition, or compute the transition and then the symmetry. So the dynamics of the MDP that describes this robotic manipulation problem are equivariant. Okay, really, it's not as subtle, but an important point that you might miss, or maybe not, is that the symmetry in the environment is heavily dependent on the state and action representation. By which I mean, like, if the input to the model was really just this image, right? Notice that this rotation is weird, right? The block moved 90 degrees around some point, but the robot is anchored to the table in some way, and that never changes in our distribution, right? Additionally, if this action is given by various torques along the motors in the robotic arm, right? It's extremely unclear to say how those torques transform under a 90-degree rotation of the coordinate, right? Okay? However, you can imagine, like, for simplicity, given that people have been doing this for a while and working on engineering this problem for a while, that you might have an environment where you have reliable, like, say, X, Y, Z coordinates for the position of this block that ignore the robotic arm. And maybe I can actually give this action as sort of like a delta pose on the end effector instead of having to worry about the actual like power that I need to apply to various motors. Like in fact, like the companies that manufacture this arm, like part of what they're trying to sell you is how good their software is. They say, buy our arm, all you have to do is say delta X, delta Y, and we'll figure out what powers to use. So it's an ongoing question what level of control might be optimal for learning, but we can accept that that's a reasonable thing to be given. Okay, and then I'll just skip this. This basically says, like, if I try to use kind of symmetry in deep reinforcement learning, it will work. Like, if I have symmetries in the environment in which I'm trying to do reinforcement learning, then the sort of policy that I'm trying to learn should involve those symmetries. So in other words, I can learn a robotic control system and I can learn it with an equivariant neural network. And that will correctly describe what's called the optimal policy. Okay, so here's an example, and I think this really helps to illustrate why the equivariance is helpful, right? So this is a simulated drawer opening task, right? And the robot needs to learn to open the drawer by trial and error over many iterations. And what it's trying to do is develop a policy that can generalize to any possible like orientation the drawer might appear in, right? And what we're doing is we're applying SE2 symmetry to the problem. So we have rotations and translations, right? Yeah.
Yeah, very interesting. But I wonder, actually, this robot, the rotation is not always in the same direction. So if you have rotation on the x-axis versus y-axis, the result will not be for them if you have y-axis versus x-axis. So how do you generalize, the non-commutability of the SO2 rotation?
Right.
So such a complicated.
That's a good question. So like we're mostly abstracting it away. So we're representing sort of like to us, we're representing the robot arm as just like having an SE3 pose, and we're not worried about sort of the different kinematics of the arm itself, which is more or less relevant depending on the problem you're considering. So for us, like the validity of that modeling approach is in the performance that we realize, but there are certainly problems in which kinematics are important, where if we didn't assume that those things were equivalent, we would get boosted performance. So it's an ongoing sort of problem. But just for oh. Okay, yeah. So, but consider the dimensionality of the problem in this case, right? The space we're trying to generalize over, the drawer can be in, actually is parameterized by SE2 itself, translations and rotations. So what that means is, if for the equivariant model, once it has figured out how to open the drawer in one position and orientation, right? Since the model is equivariant to changes in orientation and position, it has now figured out how to open the drawer in any orientation and position. So that's exactly what you see. Whereas the conventional model basically never learns those symmetries. It has to relearn how to do this problem in every different orientation and position. Okay. We also see these it's not just an efficiency thing. So this is the model trained with behavioral cloning. So the equivariant one is on the left and the non-equivariant one is on the right, right? And when you do behavioral cloning, data is extremely expensive. It's provided by somebody manually showing you how to do things, right? Which means you have an extremely sparse coverage of sort of the state action space that you're trying to learn from, right? Which means that the model like can completely come up with nonsense policies far away from where the expert demonstrations land, and you can get sort of these embarrassing results. So, where it just doesn't work. Kind of cracks me up. Okay. All right. Here's some performance curves. These are state-of-the-art methods for reinforcement learning, also from demonstration. And all of these methods, so RAD and DRQ, use extensive data augmentation, which means that these baselines also try to incorporate symmetry, but they try to incorporate symmetry by augmenting the training set. So they're philosophically based around the idea that instead of using math to constrain the model to incorporate symmetries, it's very important to teach the model symmetries. So if we show you something, let's make sure to show the model it in every orientation or every scale so the model can learn it, right? And what we see is that that's basically insufficient for many tasks, right? It's just too inefficient of a way to teach the model to learn a thing in every single orientation, because the model never learns that these things are related. You just have to make sure you cover everything. And if there's a hole, it won't generalize. For large groups, this becomes like almost impossible. Okay, here's some on robot learning. Let me just end the robot here on this one. I think I like this a lot. So in robotics, the other thing that's really slows us down is that real robots are really slow. So like training a neural network on a GPU, yes, that's time and energy intensive, but it doesn't really compare to like actually watching a robot slowly move in the lab, right? Each of these iterations is very, very time consuming. And so when you try to train policies by trial and error on real robots, it can be like unbelievably time consuming. So here's like a benchmark on a clutter grasping challenge. And the previous record for this that was just within like the realm of, yes, we could actually do this on a real robot, was around 600 hours. So they rigged up like there's a room, I think it was at Amazon Robotics, where they put like, imagine like a row of like 20 robot arms all picking up these objects over and over again, combining model weights. You have to hire people to be there because this robot policy at the beginning drops the things off the table, right? And gets into states that need to be reset. Okay, so it takes hours, but you could do it on the real robot in around 600 hours. And once you encode the symmetries in this problem, we got this down to 1.5 hours, which fit very conveniently within the ICRA poster session. So they put a single robot in the trunk of the car and drove it to Philadelphia and set the arm up And people could, during the 2-hour poster session, come and visit the robot and watch it learn through trial and error how to do this grasping over the course of 1.5 hours. So there's this, I guess my point is like, yes, it's a quantitative thing. It's an efficiency thing that speeds things up, but it's an efficiency thing. That takes things from the realm of you could never do that to now you can do that. And so now you don't have to worry about using simulators to speed up training where there's some gap between the real world and the simulator. You're just efficient enough to actually learn on a real robot. Okay, I'm almost out of time. So what I'm going to do is I'm going to quickly sort of just touch on 2 or 3 other applications without getting too deeply into them. So this is a pose prediction problem where you're supposed to take a 2D image and tell me what the 3D pose of an object is. So it's 3D reasoning from 2D images. And here we propose the idea that equivariant methods can be paired with non-equivariant methods to do 3D reasoning on non-3D data. And the result is state-of-the-art performance on these computer vision benchmarks, and also really cool pictures like this that say that these equivariant models were able to understand the symmetries of objects and represent the uncertainty over the distribution of poses. I love these pictures. Here's another example where we're working with collaborators to do radar modeling. So we're trying to either understand what is the radar signature of some object, and we want to generalize over all sorts of geometries, or maybe given the radar signature, what is the shape of that object, right? And so that's a problem governed by the physical dynamics of radar response and Maxwell's equations. And so you can take the symmetries of that problem and you can build a neural network that incorporates the symmetries of Maxwell's equations, and then you can dramatically boost the performance of your radar model. And since these radar signatures can be sparse and expensive to compute and quite noisy, if you can make do with much less data, then you're very happy. Okay. And then I just mentioned that I've started collaborating with Jonathan Blazek and Schnee to work on an Astro problem, which I don't know that much about, but we started to see some initial success in terms of modeling this area that is intrinsic alignment. So many of you maybe know more about it than I do, but my understanding is that the goal is to understand the correlation in various galaxy shapes and positions in order to create a baseline with which to measure weak gravitational lensing effects. And so this is the original method for this was a very expensive computation in which they basically simulated a universe based off some cosmic values, and then you get some distribution that you can measure these correlation functions statistically, but it's very expensive and so it's inefficient. We're not going to be able to do it over all the values of the cosmic parameters that we want. And so we're treating a neural network with some surrogates, and hopefully we'll build some symmetry in, and it will be very efficient to train. And so here are my collaborators that work with me on these various projects. And that's it. Any questions?
Thanks, Robin. That was so cool. Are there any questions? No? Yeah, go ahead.
It's a little bit very ignorant. I don't know what take a non-equivariant model and kind of clean it up by applying some coordinate transformations to get it, which you learn from.
Yeah, that's a good question. I could imagine at least 2 ways of doing that.
Let me repeat the question first.
Oh, sure, yeah.
So the question is there a way to take a non-equivariant model and then make it equivariant by adding the symmetries later in the process? Okay, something like that, no?
Yes.
Okay.
Yeah, so the hello world test case I always consider is, well, maybe this is not a good idea. I'll just explain so the 2 ways that I can picture to do it are, one is you could take the whole model, okay? And you could, suppose you wanted to be invariant rotation. So you could train some model, right? And then you could take the model and you could pass say you wanted to be invariant, an image classification model. So a dog is a dog no matter how I rotate the input image, right? So what I could do is then I could take my trained model and I could pass the dog at the image at every sort of orientation in. I could look at all the outputs and then I could pick some invariant scheme, like for example, averaging the probabilities. And then I could look at the output and then that sort of model built off the other one would be invariant. Okay, but you have to evaluate the whole forward model many times. And also like, there wouldn't be any sense in which the model had like learned the symmetries. You sort of be applying that post hoc. The other thing you could do is you could maybe take this thing from way in the beginning when I showed like the weight sharing scheme. Remember that 4x2 matrix with the repeated weights? So you could take the weight that you had learned and you could sort of project onto that shared weight subspace. So you could symmetrize the layers of your network. And I never tried it and I don't know anyone who did, so I don't know, maybe try it. Tell me how it works. Yeah.
Are there any questions in the Zoom too? But go ahead, Wally.
So you've shown this idea of the scale invariance.
Yeah.
Where all the person thought that really, really nice idea, and especially for computers. But
Yeah.
They're just clear on various scales because they're further away.
Yeah.
But as far as I know, it's not really used. Why?
I mean, there are a couple examples of it. I will say, you know, like I would say whether something has, I don't know, whether something has or hasn't been used is a related but distinct thing from whether it's a good idea. But
In a general level, I think.
Scale, I will say there are maybe some reasons I could venture on why scale equivariance is used less in vision. So one is like when you have gridded data, like you know, these images of pixels, you know, there's information destruction when I scale down, right? So that means it's not actually perfectly scale equivariant, it's at best approximate, right? Because I have loss of information when I scale down, so it's not exactly the same problem. The other is like, and so these it's not aliasing, but basically just like the loss of information due to data discretization is a huge problem in that area. Also, this group is not compact, which means like, you know, early on I said I was basically approximating an integral over a non-compact space. So like, you know, there's no distribution over scales that will work, and I need to choose these scales in a certain way. And there's some like, you know, so I'm adding further discretization besides the spatial discretization along the scale axis. So that's sort of hard. And yeah, I mean, basically we do know that performance can be improved, but there's all these like choices and loss of information challenges. And so it can make it harder, right, to tune the model. And people don't want to, you know, that's a real cost. Harder to tune models are bad.
So it relates to the thing that you mentioned before, they're not necessarily easier to train.
Yeah, they're not necessarily easier to train than train. So there's always some trade-off, you know what I mean? Like, I'm not gonna pretend that it's, there are domains where involving these symmetries is so powerful, right? You just like, I can sort of guarantee successful research papers in certain cases. Like I just know, like if there's some like physical dynamics problem with like some low-lying symmetries that no one has tried to exploit in this way, or maybe like augmentations have shown improvement, like we're gonna win, right? And so like I know that. But then like, you know, I have scaling symmetries with like highly discretized data, you know what I mean? And like maybe the augmentation doesn't help that much. It's like a little bit more of a toss up on whether it's gonna like be worth it, right, in the trade-off.
I think, is there anything on Zoom now, right? Okay, I think we can continue discussions over lunch.
Yeah.
Anyway, we have like half an hour to network. So I will thank Robin again. Of lunch.